This first video of control. Okay, I'll be splitting the videos into two or three parts. Okay, the first part is actually talking about definitions. Okay, these are all the definitions, and then we'll talk about more on equations, which is also part of definition. And nonetheless, the whole purpose of the whole lesson one is to introduce you to all the relevant equations and definitions that we'll be using in the future. Okay, so these are all the things you need to remember when you set up your basic things right. Then perhaps in the future you have no problem in understanding all the stuff that if your basic is not strong, you're dead lah, so therefore I'm here to talk about the basic. So the first step I want to do is to actually introduce you the basic definitions. So in this first video I'll just cover this one will do, and then next video I'll just talk about the rest, and it'll be like 2 or 3 videos. So let's start with complex numbers. Complex number is okay, so I assume you already know this, so I'm not going to talk about it. And then Laplace-Meinhof theorem is just stating that you're just going from, this should be in your modeling, so if you don't know, okay, so it should be your steady state of your the value when you're after you oscillate. Okay, typically when you start, you're just going in this direction and then it oscillates, and then eventually you dies down to some values. So when you die down to some values, when t is infinity, okay, this is the value that we actually are looking for. So therefore, this is actually our final value here, our final value. Okay. So the final value theorem states that if t is towards infinity, and therefore the limit to s is equals to 0. Okay. So in the time domain it's towards infinity, but in the Laplace domain s is towards 0. So with this said, you can actually do this example, and this example should be end up it should be 0. Okay, it shouldn't be this. Okay, the final value theorem shouldn't be this value, I would think so, because if you were to take the final value theorem of the output itself, okay, you know that this is 0 and this is 0, so therefore 0 times whatever thing, whatever value, you'll go to infinity, so therefore this whole thing won't work. And this is why I think they might have used the wrong thing, I think. But nonetheless, if you follow you follow this part of the example, you're taking s to 0, so this one will become 0, and therefore the final value theorem for in this case, okay, is actually this value over here. So therefore it's pretty easy, it's just finding the final value of your graph itself. Okay, so it's just finding the final value over here. So this is the transient state, and this is the the steady state. And then hold on, and then we talk about prototype signals. Okay, hold on a while. Prototype signals is to actually tell you that there are step and ramp input and other functions as an input to actually test the system. So and also tells you that normally we are looking for the error, okay, et, or the the control signal. Later in the future we'll talk about it, but just to let you know, the final value theorem is related also. So since the final value of the output is usually infinite, which is in this case it should be infinity, but yeah, they actually took the transfer function. Okay, this is actually transfer function. 1 over s multiplied by this is equals to output. Okay, so if you remember, the definition for transfer function is actually output over input. So if you bring this input, okay, multiply by this, you'll get output, right? So therefore this is what we are talking about. So the transfer function itself is this thing over here, and then the input itself is the step input, therefore it's 1 over s. Okay, the step input is this one. So yeah, hopefully I didn't I think you already start to confuse yourself. I mean, I have already confused you. So yeah, let's not talk more. So and then now talk about poles and zeros. Poles and zeros is pretty easy. The definition is, hold on a while. So the poles and zeros is just talking about the transfer function. G of s is equals to the y of s, the output over the input. Okay. So the zeros and poles, okay, is that whatever things that make this equation zero is called zero. So which portion, okay, is it the numerator or the denominator will make this whole equation to become zero? It is actually numerator, because whatever thing divided by zero, okay, is equals to zero, okay, even equals to zero, okay. So the numerator from this aspect, the zeros, okay, zeros stands for when you make the equation zero, you make it, it is zero. So therefore, the output itself is actually zeros, while the input itself is the I would say that the numerator is the numerate whatever thing that makes the numerator zero is zeros, and whatever thing that makes the denominator zero is called the poles. So it's meaning that if this is zero, the whole equation will go to infinity, right? So we don't want it to go to infinity because it will make the whole system be very unstable. So our key concern is not to let the whole equation become zero nor let it become infinity. And our most concerned things about all of this is that make sure that no equation goes to infinity. And this is why it explains the reason behind why they actually find the final value theorem for this part instead of this part. Okay, because the problem doesn't lies with it doesn't lie with the input. Okay, it doesn't lie with step input, impulse input or what. Everything lies with the transfer function. If the transfer function is not set right, if you take it to a final value theorem with some step input, you'll eventually get some infinity, which is what we don't want. So therefore you have to first therefore final value theorem is a so-called a test to test whether is your equation going to infinity. If it's going to infinity, you have to change some of the configuration in the transfer function in order when you multiply with step input or whatever input you want, make sure it doesn't goes to infinity. Okay, if it goes to zero, it's good. Okay, so just to say again, I actually say wrong. Just that whatever thing that goes to zero, okay, which is the zeros, it's okay. Whatever thing that goes to infinity is not okay. Okay, so this is one thing. So what is zeros and poles? Okay, zeros is whatever thing make the numerator zero is zero. Whatever thing that makes the denominator zero is pole. Okay, or whatever thing that makes the whole equation become infinity and then the denominator is zero is pole. So yeah. So I believe I already cleared all these things. Okay, there are a few other stuff, like let's say the cover-up rule for transfer function when you are doing with a lot of Laplace transfer function, okay, complex functions, then you have to use maybe a partial fraction or what. So these are the etc. that I'm talking about, which is you have already learned in modeling. So I'm not going to talk about it. So in the next video, I'll just talk about how poles and zeros are being so graphically how does poles and zeros look like, and how they are being utilized in first and second order responses. So I shall see you there.